We're going to look at a foundation for doing inequalities. These are the inequality signs, all the signs that imply that two things are not equal. Probably seen these before. So, let's look at these two numbers, 11 and 20. How would you compare 11 to 20? Well, clearly it is less than, so we would grab this sign right here. We'd say, well, 11 is less than 20. Now, by the way, you can read it the other way. You can say that 20 is greater than 11 because the sign implies that the smaller number is this way and the bigger number is this way. Remember where the alligator mouth is? But technically that's a less than sign, but we have the right to say 11 is less than 20 or 20 is greater than 11. That comes into play later when we're going to start to say that 5 is less than x. We can go backwards and say that x is greater than 5. So be comfortable going both ways. Now 4 plus 8, that's 12 and that's 9. So how do they compare to each other? Well, 12 is greater than 9, so we could use this sign right here. Now technically, do you also agree we could even use this sign if we wanted to? We could say that it is also greater than or equal to the 9. That would not be an incorrect statement. Now think about this. Is it ever possible for these two quantities to be equal to each other? The answer, if you think it through, should be no. They should not be equal because you're adding 3 to the same value that you're adding 2 to, so they should be not equal. So that's how these two quantities relate to each other. They're not equal to one another. Okay, now graph the solution to x minus 2 equals 0. Well, if we use some good math, the addition property of equality, then we're going to end up with x plus 0, which is just x equals 2. Now, this may seem simple. Let's graph every possible solution for x. Well, the only value we can put in for x is 2, so we're done. We have graphed the solution to this equation. But now contrast that with this. Graph the solution or solutions to this inequality. Well, again, we're going to get x by itself because we have the left side and the right side of the inequality. If you want to, again, put a little dotted line there separating the two sides. We'll add 2 to get x by itself. We do the same thing to the other side. We'll add 2. We're left with x is greater than 2. Now, if we start to think about some numbers that would make this statement true and we start graphing them on the line, every number we can think in to put for x gets a dot. X is greater than 2. We could choose 3 because 3 is greater than 2. We could choose 4. It's greater than 2. How about 7? It's greater than 2. In fact, we can do decimal numbers. We could put in 3.6 or 3.7 or 3.8. And what starts to happen after we put in all these dots is they just form a straight line. So that's why we're taught to just fill in the line with infinitely many dots. Every dot is a solution to this equation. But where's the boundary? Where's the boundary between the solutions and the non-solutions? It's at 2. So we can have any number that's just a little bit greater than 2, like 2.05, 2.1. Any of those numbers work, but as mathematicians, to stipulate that x cannot be 2, we put an open circle at 2. So this is called an open interval. We should put an open circle at 2, and we can have this bad boy going this way right here. Open interval. Okay, now, if we do this, if we say, well now x minus 2 is greater than or equal to 0, again, we're going to add 2 to both sides, and we have x is greater than or equal to 2, and we're going to say, okay, again, how many different values can you put in for x? Well, any number that's greater than or equal to 2 works. We'll put a solid dot for every number we could put in for x. We can put in 5, 4.9, 4.8, 3 point whatever. We can put a whole bunch of dots in here, but in the end what happens is we say any one of these points works, so we start to fill these in. All these dots form a straight line. The boundary's at 2. None of the numbers below 2 work. Every number greater than 2 works. The boundary's at 2, and we say that x can be greater than or equal to 2. So to stipulate that 2 is also a solution, we put a dot there as well, a closed dot. And then all the points above here are solutions. So the way we show it is a closed dot with a constant line going to the right, and we put an arrow here saying it just keeps going towards infinity. This is called a closed interval. We close it off with a dot because 2 is also a solution. X could be greater than 2, but it can also equal 2. Closed interval, and remember, open interval. X cannot be 2, so an open circle at 2. Well, then we go here, we need interval notation. A closed interval is depicted with brackets. Open intervals are depicted with parentheses. So right here, x is greater than 2, we showed this graph, open at 2, so a parenthesis at 2, that's where the boundary is, that's where the solutions are, from 2 and everything above going to infinity. Now, we never make it to infinity, we're just talking about the numbers increasing without bound. There's no boundary, they just keep going and going to infinity, so that's the idea. So there's also an open interval there because you never make it to infinity. The idea is that the numbers just keep getting bigger and bigger. So open interval. But this guy, x is greater than or equal to 2, we set a closed interval there because x can equal 2, and that's why we use a bracket at the boundary where the solutions begin. So it's a bracket at 2, it's closed at 2, open to infinity. So, if we look at this graph, we say write an inequality statement for this thing. Okay, what would it be? It would be x is less than or equal to -3. Interpret it. What would we say? Well, x is less than or equal to -3, or we can say that x is at most -3, and then interval notation, well, let's take a look. These are our solutions. X is less than or equal to 3. We put an equal sign here because that's closed off. It's a closed interval. That's why we have a closed boundary at -3 and then everything to negative infinity. Keep in mind, this is the low end of the interval up to the high end of the interval. So we start at negative infinity and we go up to -3 and include -3. Now here's an important thing. You want to be able to say when it's less than or equal to -3, that implies that x is at most -3. So the biggest x can be is -3, and it could be anything below it. So x is at most -3. Now contrast that with this. Closed interval from -1 and above. So what can we say? We can say that x is greater than or equal to -1. We can say that x is at least -1. The very least x can be is -1. It can't be any less than that. So it's at the least -1 or any number above it. And again, it's a closed interval. Remember to put the low end, the smallest end of the interval here, and the high end here. It's closed at -1, bracket, and then it just goes to infinity. Let's graph this. X is less than 4. So we go to a number line. We put 4 here, maybe 0 down here. It's open at 4. So we put an open circle stipulating you can't pick 4, but you can pick any number less than 4. But instead of just putting a whole bunch of zeros or dots in there, we can just say it's open at 4 and it's any number down below. State what this means. Well, it's less than 4. X is just less than 4. Write this using interval notation. This interval is open. This interval is also open. Down here, this starts at negative infinity. You're just approaching it that way. That's the small end of the interval. The high end of the interval is 4. So that's open interval notation for less than 4. Define a variable and write an inequality in interval notation to model the situation. Hey, as young students, let's be wise. When we start getting word problems, I might even take a colored pencil. I'm going to do a couple things. It says define a variable. That's one thing. Then it says, and now we need to write an inequality in interval notation. And I might circle interval notation. This is called annotating the problem. We want to just differentiate and say, what is it that we have to do? Got to first define a variable, and then we have to write an inequality in interval notation to model this situation. All right. The height of the balloon must be at 12 feet or higher. It's the height of the balloon that can vary. The height can vary, so that's our variable. So our variable would be the height of the balloon. That's our variable right here, the height of the balloon. Now it must be at 12 feet or higher. So interval notation would say we can be at 12 feet closed or higher. it could theoretically go to infinity, although I think there's a limit to how high the balloon could actually go. Technically speaking, that's what we've done. Now, you know what? I guess to be true to this, since interval notation, that was in red, I should say this was my second task. So let me write that in red, saying that's the second thing I had to do, was write this inequality in interval notation. By the way, if we were going to say this using a statement, a math statement, it would be that x would be greater than or equal to 12. This is equivalent to that. All right, finally, test scores. We can see that what this implies is all the test scores are in between 70 and 95. So that's what we say, test scores were between 70 and 95. What that means is we can put our variable here, and it is between 70 and 95. So what this means, it's two statements in one. It means that 70 must be less than the test score that we had, or that x, the test score, is greater than 70. Remember, we can read it the other way. And at the same time, it's got to be true that the test scores we had were less than 95. So for both of those statements to be true and come together in one statement, it implies that x would have to be between 70 and 95. We can't pick a score. We know there was no score like 60 because even though 60 is less than 95, it's not true that 70 is less than 60. So both statements have to be true. It's called a compound inequality, and it can be written in just one big statement like that. So this implies that the test scores are between 70 and 95. So lastly, if we say that the test scores were between 70 and 95 inclusive, it means that 70 and 95 were among the test scores, and so it's a closed interval, closed at 70, closed at 95, and so this would imply that, oh, we're going from 70 to 95 inclusive, it's a closed interval. So that's it. That's a beginning idea surrounding some of the basics of inequalities.